Thank you. So thank you very much to the organizers for inviting me, and I regret I'm not there in person, but fortunately it still works with the speed of light. So this is a lecture in honor of Toshiyuki Kobayashi, and the title is Discrete Series and their Symmetry Breaking Operators. This is based on joint work with Jorge Vargas, but it builds heavily on results by Kobayashi. Now, as we all know, mathematics is a social science, and I think no one more than Kobayashi has shown what this means in terms of connecting to people, connecting various groups of people, connecting various areas in this topic. So my lecture will be like this. I'll start with some personal remarks on the career by Kobayashi. Then I'll talk about discrete series representations, some of the models that are known, and some of the geometry behind. And some of the tools that we use instead of reproducing kernels. So there'll be some reproducing kernels in the talk. And just to give you some headline for the results, that'll be that for symmetric pairs, G and H reductive groups, we'll get admissibility, and I'll get to that, the notion by Kobayashi, via the notion of differential symmetry breaking operators. So that'll be the first half. And the second half about some cusp condition on the spherical functions. So there'll be some notion of spherical functions that will allow us to detect admissibility. Now, so very briefly, this is going to be very brief. Kobayashi, he had, I can see, a very early vision on harmonic analysis and representation theory. So I guess I first met Kobayashi in '89 at Kawaguchi-ko. There was a beautiful conference center and a beautiful conference near Mount Fuji. And already then he did some spectacular results. He has done many spectacular results on both the algebraic, geometric, and analytic aspects of the representation theory of reductive Lie groups. And I would like to emphasize here that we are seeing work both in the algebraic aspects, very algebraic things, Lie algebraic things, geometric things, and also deep analytic aspects. And I can only mention a few highlights. Some of my personal highlights. So in '89 already, Kobayashi had the notion of proper actions on a homogeneous space for a Lie group G. The notion of proper actions, which then led to the notion of Clifford-Klein forms. So this was already known for the case of G mod K, a maximal compact modular, the action of a discrete group gamma, but then he extended the results of Margulis to more Clifford-Klein forms, so could find compact space forms based on affine symmetric spaces G mod H, so not necessarily Riemannian, but pseudo-Riemannian. Then he had a long paper on Stiefel manifolds for the groups UPQ over fields, local fields, wheels and complexes and quaternions, so UPQ mod UP minus M comma Q. So this is not a symmetric space anymore, but he still could confine some discrete series representations. So in a very deep way. This was one of those spectacular results. Then in '94, we saw the study of AQ lambda modules and their branching laws in a convenient setting. So this is also where Kobayashi found what he saw was a convenient setting, namely the setting of admissibility and discrete decomposability, where you could describe these things in algebraic ways and also in analytic ways. Then came in 2004 the notion of visible actions and multiplicity freeness using this notion. Then 11, the Schrödinger model for the minimal representation of OPQ. In 12, the classification of discretely decomposable AQ lambdas for reductive symmetric pairs with Yoshiki and Toshiyuki. And then the systematic notion, together with Pevsner and Birgit on symmetry breaking operators, for example, for the pair O1n plus 1 containing O1n. So here, this notion became very much studied. Then in 2015, the notion of tempered representations sitting inside L2 of G mod H for G semi-simple and H a reductive subgroup. So here a long series of papers leading up to the classification of which reductive which semi-simple modular reductive subgroups could be tempered. So some algebraic, geometric, and analytic notions to detect this. And then one of his later works, and still very interesting, restrictions of small representations, and much more. So Kobayashi has been very active as a teacher and mentor for many students and postdocs, and as a co-author, in addition to giving many splendid lectures around the world. So we all know this, that he has been very, so as I said, mathematics is a social science. So this is where he has really contributed, giving lectures on all his many ideas and talks. And I should also say that his career has been also one of a teacher, one career as a very good teacher. I was visiting University of Tokyo 7 years ago in the spring semester, and I could see how active he was, teaching a graduate course and also teaching other courses, even teaching courses for students for different faculties. So he was giving very successful lectures for, I think, even students of law and other departments, giving excellent examples and, being a very, very productive teacher. So let me just say that he's very highly respected in the West as Toshi, but in Japan, of course, you respect Kobayashi Sensei, which means teacher or master. So this is what we do. Okay, so let me get to the setting of my lecture here. So G will be a linear connected semi-simple Lie group. K will be a maximal compact, and there'll be a maximal torus in K. And the assumption would be here that T is a Cartan subgroup of G, so that G has a discrete series of representations parameterized by lambda in a lattice. So this is the theory of Harish-Chandra. So the very deep notions of discrete series. So each V lambda, sometimes we call this an irreducible square-integrable representation, unitary. So by definition, it's equivalent to a closed left-invariant subspace of L2 of G. And yes. Of course, what it means in practical terms is that you have to look for matrix coefficients that are square integrable over the group. So this is the notion of discrete series representations. Now let's look at the Cartan decomposition of the Lie algebra in the complex Lie algebra of K, and the P, the Cartan, and the root system. So we have a root system which divides itself into the compact roots and the non-compact roots. Delta, I'll denote by delta the positive roots for the compact root system, and rho half the sum of the positive roots. And then we have the definition of the so-called Harish-Chandra parameter. So this is an element in the I times the real dual of the torus. So the scalar product, or this is, or well, the lambda. So we should think of the killing form here as defining an inner product. So lambda comma alpha. So lambda should be regular with respect to all the roots. So sit in the open chambers, and then the condition is that lambda plus rho lifts to a character of T. And then if you look at those that are delta dominant, this gives you a bijection to the equivalence classes of discrete series representations with infinitesimal character lambda. So here I'm not going to go into the details of this, but you remember the infinitesimal character is a character on the center of the universal developing algebra, and it's given by the functionals on the invariant polynomials on the Cartan. Okay, so here's a little example. So think of G as SU2, 1. This has a discrete series. Indeed, it has a holomorphic discrete series. It has an anti-holomorphic discrete series, and it has a large discrete series. So the green chamber here would be the chamber where we take as positive roots this n and this n. The holomorphic discrete series will be where we take as positive roots, positive simple roots, this compact one, and the non-compact one. So notice that there's exactly one non-compact simple root for this system where we look at the holomorphic discrete series and the anti-holomorphic. There'll be also a system where there's exactly one non-compact simple root and the compact root. And so these are the three families of discrete series for SU21. So we should think that each family in this way, so corresponding to a chamber, has its own personality, has its own way of of being realized. Okay, these have different Gelfand-Kirchhoff dimensions. So the holomorphic ones have Gelfand-Kirchhoff dimension 2, and the green series, the large discrete series, has Gelfand-Kirchhoff dimension 3. So this is a notion of how big the representations are. Okay, and so here the positive system is the one that once you choose the lambda, you take the positive system. As I said, you take those for which the inner product with lambda is positive. Now it's a nice fact due to Wogan that each such discrete series has a unique lowest k type. So we normally call it tau and w. So w the space. This is infinitesimal character lambda plus rho n. And this determines pi lambda up to unitary equivalence. So to characterize a discrete series, it's enough just to give the lowest k type. Now, one of the early mysteries in the theory was how to construct pi lambda. So Herrstrand out of thin air constructed the discrete series by means of their distribution characters. And then he could use them, that he could see that it sufficed to decompose the regular representation of the group. So L2 or G, that whole Hilbert space could be decomposed using, in particular, this discrete series. So he had enough discrete series just by the distribution characters, and then the characters of the principal series, that was enough to decompose the Dirac distribution. But it was a mystery in a way in the old days how to construct the pi lambda, except the holomorphic, which Herrstrand did very, very precisely, the construction. Of course, nowadays, we have several ways to construct it. We have the algebraic category, the right functor module, the AQ lambda by cohomological induction. This is as a Herrstrand module, so as a representation of K, and then an action of the Lie algebra G in a compatible way, and with a built-in invariant Hermitian form, which is positive definite. So this makes it an infinitesimally unitary representation, and then by Herrstrand, this is a representation of the group, which is unitary. There's also constructions in the category of smooth Fréchet representations, so-called globalizations. Sometimes you can simply take a Herrstrand module. If it has sufficient growth of the matrix coefficients, you can then form a globalization, which would then be a smooth Fréchet representation, and it typically lives in some D-bar cohomology space. It could be on, for example, G mod T in some degree. But then what we'll focus on today is really the category of Hilbert spaces. So after all, a Hilbert space is the place where the representation, when it's unitary, really lives. And so here's the Hotter construction. So the Hotter construction is that you take the space H2, which is a subspace of L2 functions with values in W. They transform in the right way under K. So this makes it a section of that homogeneous vector bundle on G mod K. And then you take the Casimir operator, omega G, and you act from the right or the left, it doesn't matter. And then F should be an eigenfunction with eigenvalue lambda minus rho rho for this operator. So this is the Hotter construction. And you see it's built as a Hilbert space. So the fact is that, okay, so it's actually a closed subspace of the L2 sections of the homogeneous vector bundle. And the fact is that this is an elliptic operator. All sections are automatically smooth for this reason. And also for the same reason, point evaluation is continuous. And therefore, you have a reproducing kernel, which is just a function of two variables with endomorphisms in W as values. And it satisfies that if you fix the X, then as a function of the first variable, it belongs to the space. And also, if you form it if you look at it as an integral kernel, so this integral makes sense because f of y is a section of the bundle. If you take a section of the bundle, just an L2 section, and then this operation, this integral kernel, will give for you the orthogonal projection from L2 down to L2 as G. So think of the holomorphic case. If these were holomorphic L2 functions on a bounded domain, then we know in the same way that we have a reproducing kernel by the same mechanism. Okay, so now the setting that we'll study here is we'll take so G was this linear simple Lie group. H will be a closed reductive subgroup. L will be a maximal compact in H. This will be the assumption. And we let U be a maximal torus in L and also a Cartan subgroup of H. So this means that not only does G have a discrete series, also H has a discrete series. And the problem that Kobayashi has, contributed to a lot is to understand branching laws in this case. So in general, the Hilbert space will decompose under the action of H as a direct integral of Hilbert spaces. And there will be some multiplicities that could be finite or infinite, and there will be some measure. If the measure has atomic points, if there's a discrete spectrum, that means that some of these are just a direct sum. There could be a direct sum part and a direct integral part. And the direct sum part will be the discrete series. We'll call this the discrete series. And in general, this is, of course, a deep problem to decompose. So already a special case would be if there's a single self-adjoint operator, then, of course, to decompose the space is a deep problem in spectral theory, and to do this explicitly. However, and also what Kobayashi initiated was to find explicit symmetry breaking operators. Even if there's a continuous spectrum, it still could be interesting to find symmetry breaking on the smooth vectors. So on the smooth vectors down to smooth vectors in each piece here, you still could be looking for symmetry breaking operators, which by definition are H equivariant operators. Okay, and so another problem here would be if there's a discrete series of H with a lowest K type, find if possible a linear continuous H map. So this would be our definition of a symmetry breaking operator today. That will be in the Hilbert category from the Hilbert space H2 for G to H2 of H, which should be continuous and linear. And so this is where the Kobayashi, what he was zooming in on very early, would be to define a unitary representation to be discretely decomposable over H if there exists an orthogonal family of closed H-invariant H-irreducible subspaces of V, so that the closure of its algebraic sum is equal to V. So simply filling out the whole thing. And then even stronger, admissible if in addition each irreducible H factor has finite multiplicity. Now notice that this is a strong it's a strong condition, because of course every time, for example, you have a compact group, it will be acting on a Hilbert space, it will be discretely decomposable. But to have the admissibility is a deep condition. So this was what Hershender showed for a maximal compact subgroup of a reductive group that is automatically admissible. A unitary reducible for the big group is automatically admissible for the maximal compact subgroup. So this is a very, very, very strong. And our aim is to find concrete symmetry breaking operators in the admissible situation. And we will look for them as integral operators, and we look for them as differential operators. So integral integral operators similar to what we saw before, with a projection on the H2 of H, and also some differential operators. And now for the lowest K type of pi lambda, there's an important function which is given like this. So PW is just the projection from the Hilbert space down to W, down to the lowest K type. Then you act by the representation, and then you project back on the lowest K type W. And then there's a normalization quantity here, which is the formal dimension of pi lambda. Then K lambda can be expressed conveniently in terms of the spherical function. So this is now a matrix valued function and its trace. So the trace, the little K lambda will be the trace of K lambda. We call this the trace spherical function. And then the link between the two. And now what we're looking for is what Kobayashi was defining already. What do we mean by a differential operator, going from the, say, the smooth sections of the big homogeneous bundle to the smooth sections of the small homogeneous bundle, so on the G and on the H. So by definition, a differential operator is an expression like this, where you differentiate from the right your function by elements in the universal developing algebra, differentiate and restrict to H. And then you take an inner product in W with some vectors in W, some constants D, A, B, C, and then some vectors Z, A in E. So where you land. So you go from having values in W to having values in E of these functions. And if this is a finite sum, this is what we call a differential operator. Sometimes we can even, well, we could run into infinite order differential operators, then this would be an infinite sum, but we'll be looking at finite sums. And now there's a nice conjecture by Kobayashi to what extent in this setting here, or even in a more general setting of AQ lambdas, do we have a differential operator to give us the symmetry breaking operators? Could that happen? And indeed, there's a theorem which is inspired by this Kobayashi conjecture, namely in this setting as above, the pi lambda would be H admissible if and only if for every irreducible sigma Z of L, so this was the maximal compact in H, so lowest K type of H, any continuous H map from the H2G to the H2H is a differential operator. So if it's admissible, then there will be a differential operator that implements the symmetry breaking, and vice versa. If every symmetry breaking is given by a differential operator, then it's admissible. And let me just give a small example of this this type of thing. If we take the quadratic composition of G and the similar quadratic composition of H, here's H the L plus P prime, and we look at the normal space P mod P prime, we just could take a normal complement to P prime, and we take its n-symmetric power. And now we let tau n be the action of L in the space of homomorphisms from this symmetric power to W. So notice that L acts both on P, it keeps P prime fixed, so it acts on the quotient, and it acts on W. And then we take this restriction operator. So here's a restriction where you differentiate your function from the right. So this is the symmetrization map. So it goes from the symmetric tensor power of G to the universal developing algebra, just a symmetrization map. And now we can differentiate from the right. And when we do this, we get a, well, you see what we get here. So we are differentiating first from the right and then restricting. And so this gives us a map from L2 of G, so the discrete series are on the big group, to the smaller homogeneous bundle now with fibers, this Helm space. And the point is that this is H equivariant and continuous, so this is a bounded map. So this builds, in fact, on the Gunze-Stein phenomenon that there's an estimate for the reproducing kernel of G that allows you to conclude that this is H equivariant and continuous. And this integral kernel, so it's an integral kernel map. It's given by, you simply differentiate in the second variable from the right, this K lambda YH that we had before, the reproducing kernel. So let me just give you a few steps in the proof of the theorem from before, the one connecting admissibility to having a differential operator. So some of the steps are just here. So suppose you had such a symmetry breaking operator, and suppose it was given by a kernel. So this is what it means to have been given by a kernel, right? There's a kernel of two variables. So that as an integral operator, you just integrate the y away, and that gives you, the operator. And if this is given by in such a way that this makes sense, so as a function of y, it's L2, so this integral makes sense. And if it's K finite, so this is the important thing, if this is K finite, then this is a differential operator, and then it's automatically continuous in the L2 topology. Okay, and this builds on the deep observation by Kobayashi that the admissibility can be expressed in this way, that the K finite vectors is the same as the L finite vectors. This is a deep statement. And also, if you look at the discrete part of the L2 of H, so you take the L2 sections of the small bundle, or some representation U of L and E, then the discrete spectrum it's always a finite sum of eigenspaces for the H Casimir, and point evaluation is continuous. So this is just like a finite sum of such Harter constructions of the discrete series. Another tool that goes in is if we have a non-zero H map that goes symmetry breaking, then this is, and if this is the differential operator. So if you have a differential operator that is doing the symmetry breaking for you, then pi lambda is H discretely decomposable. Remember, this is not as strong as admissible, but it is still discretely decomposable. And then the last statement would be this, that if for some discrete series, every non-zero map is a differential operator, then the multiplicity is finite. So this in a way is combining the above steps. Okay, let's give a small example. So if G mod K is emission symmetric, and if H2 is a holomorphic discrete series, and if H mod L is a real form, so it could be that G was SUPQ and H was SOPQ, then no such bounded symmetry breaking operator is a differential operator. Then this never happens. Okay, let's see some other criteria for discrete decomposability. So recall the projection on the Harter space on the H2 closed linear subspace of L2 sections of the homogeneous bundle. So we had this projection. We had the spherical function, which was just convolution with this one, is giving us the projection. Now it's a fact due to Hertzschender that this is what's called a temporal function. So it's in Hertzschender Schwarz space. So I'm not going to defining this, but this is just modeled on the Schwarz space in Usual's Euclidean space, that all derivatives should decay in a certain way. And this certain way is really what characterizes the Schwarz space. There's a certain psi function which allows you to define this. But this is a very important space by Hertzschender. And then a function in the Schwarz space is called a cusp form. If it's integral over n, where n is the radical of a proper parabolic subgroup, and if all left translates are integrating to 0 on n, you call this a cusp form. So this was the notion that Hertzschender was using in his theory of the Planck-Schrödinger formula for the group. So we call this a cusp form. And this is in fact the closed span over the L2 Schwarz space of the discrete series. So if you look at the discrete series and you look at the corresponding L2 Schwarz space, then you get this space. And also the restriction, if you restrict cusp form to the subgroup H that we have, reductive subgroup, also equal rank subgroup, then you get another cusp form. And so our theorem concerning this is that if you have a discrete series for G with phi 0 as its lowest K type circle function, then it's equivalent to say that the restriction, this restriction map we had before, you differentiate in the normal directions and restrict. This is a cusp form on H for all n. Or you could say that pi lambda is H discretely decomposable. Or you could say that the restriction of this function in the first variable to H is a cusp form for all y and g. Or you could say that the circle function here is left, so here by z, u, g, I mean the center of the universal developing algebra of H. That should be finite. That should be z finite. Or it's equivalent to say that pi lambda is H admissible in the special case where H is symmetric. So if you have a symmetric subgroup, if it's a large subgroup, then in this case, discrete decomposability is equivalent to H admissibility. This is another one of the deep insights of Kobayashi, that if it's a symmetric subgroup, then admissibility is really, you see, this is really the strong condition. So again, think of a maximal compact subgroup. Not every compact subgroup would be admissible, but the symmetric, the maximal compact subgroup is admissible. Or rather, every representation will be admissible for this group. Look at the small example here. Again, look at G cross G. and look at the symmetric subgroup to be the diagonal. And look at the tensor product of H2 G mod G comma tau with its dual. This is now a discrete series of the G cross G. And look at the low scale type spherical function. So this is just the product of phi 0 x times phi 0 y. And the restriction to the diagonal will be strictly positive. And therefore it cannot be a cost form. You know, you cannot integrate this one to get 0 because it's positive. And hence this one is never discretely decomposable. This, of course, is not a big surprise, but it just follows in an easy way from this criterion with a cusp form. Now, here's an example that I worked out with a paper with Joe Wolf. This is the so-called Borel-Siebenthal discrete series. And so here we assume that the parameter lambda has a corresponding positive system with that same condition. Remember, in the example I showed you for SU21, there was exactly one non-compact simple root. So assume this. And also, let's take the case where G mod K is not Hermitian symmetric. Then we have a subgroup K1, an even smaller subgroup in K. And we have an intermediate group, another, that's not the same as before. We have an L tilde, so that there's a homogeneous homomorphic vector bundle over G mod K, corresponding to a high straight gamma of L. Okay, so it's a homogeneous vector bundle, so that so that pi lambda. So here there's a notion of negativity, which comes from the algebraic geometry and cohomology. So this is now realized in a double cohomology in degree S. So here S is the dimension of K mod L tilde. And the nice geometry here is that K mod L tilde is a compact Hermitian symmetric space. And pi lambda is K1 admissible. So there's a substantially smaller group, K1, inside K, for which this representation is K1 admissible. Now there's a special case which was looked at by Gross and Wallach. Let's take the case of SO2P, 2Q plus 1. So of course here the root system is a Bn, so these epsilons and the additional epsilon I. And a highest infinitesimal character lambda will be a combination of these of the usual epsilon I. And here lambda I should be in 1/2 plus z. And here's the rho. Let's see what the rho is. And so the order is just this one, just the natural order. So this is the order. So this is a positive lambda. So, and the K1 is now just the SO2P, so it's rather small. And the representations in this Borel-Siebenthal discrete series are K1 admissible. Now let's restrict this to SO2P, 2Q. This now has root system type Tn. And the roots are like this, epsilon I plus minus epsilon j. And again, the lambda, so this time the order looks like this. So the lambda 1, lambda 2, down to lambda n absolute bigger than 0. So the lambdas are now integers because the rho looks like this. Remember, the rho plus lambda had to be a character of T. And again, this is K1 admissible. And the proposition here, which was proved by Wallach and Gross Wallach, is that we have this one is H admissible. It's a multiplicity free direct sum of the pi mu H, and the interlacing pattern looks like this. This is the interlacing pattern. So this is in fact a manifestation of the so-called Gross-Prasad conjecture. And so notice that there's interlacing. So the lambdas was for the big. Is for the big one, and the mu's is for the small group. So the mu1 bigger than lambda 1. So notice that there are infinitely many mu's here. And down here in this right half of the interlacing pattern, there's only finitely many mu's. So here's for the lambda again for the big one, and the mu's is for the small one, and here's the interlacing pattern. So notice that that the second part resembles a compact branching law, right? If Q was 0, this would be a purely compact branching from SO2P plus 1 to 2P, and it would be just this interlacing pattern, finitely many. But notice that the first part of the interlacing pattern looks like the interlacing that you see in K-types. If you look for discrete series for SO2n, 1, you'll see these K-types, and the interlacing is like this. And so this will be explained in further joint work involving something we call a pseudo-dual pair. So if H is a symmetric subgroup, then we let the companion H0 be the symmetric subgroup corresponding to the Cartan evolution times sigma. So there's a slightly different symmetric subgroup. And so this is what so I write here to be explained. So in fact, in the lecture tomorrow by Jorge Vargas, he will go further into this idea of using, when you want to do the branching to a group H, symmetric subgroup H, you'll get a lot of help from the accompanying pseudo-dual group, pseudo-dual pair group H0, which is now the G sigma. So you should think of the picture in such a way that H0 and H are filling out the group. L is the intersection, that's the maximal compact in either one. And something similar will happen to the representations. In some sense, when you take the lowest K type and you act on it by the H0, sometimes sometimes it will create for you a bunch of lowest K types for the action of H. But you'll see this so this is the cliffhanger for tomorrow, that this will be explained by Vargas. Now, some of the tools, so some of the tools that we use in this thing is again, the continuous linear H maps. So this is like sometimes called by Kobayashi, this is called a holographic map, where you go from the small space to the big space. And suppose you do this in a linear way, then by the reproducing kernel property, we know this is given by a kernel. So such a map T, if it's continuous and going from the homogeneous sections on the small to the homogeneous sections of the big, it will be given by a kernel like this. So there'll be a KT X. So you integrate the H away and you get a function of X out of it. And so the idea to use this picture here to explain the branching here, the branching for this special case of SO2p, 2q to SO2p, 2q, that really remarkable branching law will be explained using this kernel here. And so the idea is to consider the restriction of this reproducing kernel, or this kernel for the map to the H cross H0. So consider this kernel in these coordinates. Now, of course, an extended problem is when there is both a discrete and a continuous spectrum in the branching, then what? Or when can we say that there is just some discrete factor, some discrete spectrum in the branching law? And now one way to say it in terms of the kernel again, so if you have a kernel for the big representation, discrete series, and a kernel for the small discrete series pi mu of H, and then if you look at this pairing, you look at the corresponding trace circle functions. Now, if the L2 inner product between a K lambda and a K mu, so that means that you restrict the K lambda to the H, and you take the L2 pairing, this will converge. If that's non-zero, then pi mu lambda, then pi mu is a discrete factor in pi lambda in the restriction. So this was observed by Vargas in 2011. And in fact, we in a very special case, we looked at this where if the big group is a spin 2n1 and the subgroup H is a 2n minus 2k, 1 times a compact factor. And you take an integral discrete series. This means that the matrix coefficients are not only L2, but they're also L1. They're integrable. Then in the branching law, there will be infinitely many discrete factors. There will be a continuous spectrum, but there will also be a infinite discrete spectrum, which will be of the form Zj tends to Wj. So Wj would just be a representation of a spin 2k. And the Zj will be a discrete series of spin 2n minus 2k. And so there'll be finite multiplicity. The W's, we can say where they come from. They come from this normal derivative business. They live in the symmetric M power of R2K, sense of the original W. And so this is just an example of what we did to calculate, using this restriction idea to calculate some discrete part of the spectrum, but even in a situation where things are not discretely decomposable. Okay, let's relax with an example from physics. Let's relax with the hydrogen atom. So here's the Schrödinger equation. Here's the Schrödinger equation for the hydrogen atom. So this, so K over R is the in 3 dimensions, just the way the distance to the origin. So you recognize the Coulomb potential minus K over R. You recognize the Laplace operator here and some physical constants, Planck constant and mass, and the energy. So we're looking for such an equation, this eigenequation. So this is in fact the spectral study of a single self-adjoint operator. This is self-adjoint in L2 over R3. So this is just trying to decompose the space into pieces under this physical operator. So the bound states will be those where psi is an L2 function and the energy is negative. And there will be some scattering states. Scattering states will be when the energy is positive. So there will be a continuous spectrum here by this half line, and there will be some discrete eigenvalues that are proportional to minus 1 over n squared, when it's 1, 2, 3, and so on. So this is the spectacular. This was part of the spectacular beginnings of quantum mechanics, where they saw the spectral lines on the spectroscopic measurements of light. Sometimes there'll be absorption lines or emission lines, and you always saw these jumps in energy between something minus 1 over n squared to something minus 1 over m squared, and they had these famous lines. So this was one of the early successes in quantum mechanics, and what was discovered very early by Vladimir Fock in 1935. He saw the following. He said, let's take a Fourier transform of such an eigenfunction. Take its Fourier transform, and now take a stereographic projection after you do the Fourier transform. Change variables, and then the equation becomes this one. Now it becomes an eigenequation for this convolution operator on the right. So psi of x should be lambda 2 pi squared. So x and x prime are points on the 3 sphere. We just compactified the 3-dimensional Euclidean space. And notice that here's this nice kernel. So the lambda is a constant. And you see that the statement from before with the energy levels being what I said, you see that statement. Well, see, that statement just corresponds to saying that the lambda here should be 1, 2, 3, and so on. And indeed, this is what Vladimir Fock could calculate in a very nice way, that the spherical harmonics, if psi of x is a spherical harmonic, here psi, and psi is a spherical harmonic of degree n, then exactly the lambda that's here in this equation will be n, 1, 2, 3. So spherical harmonics is in some sense the bound states of the hydrogen atom are in some sense just given by spherical harmonics. But this is after you Fourier transform. So I think this is a nice trick. He did this in order to explain the hidden symmetry in the hydrogen atom, namely or the Kepler problem. You could also call this the Kepler problem. There's a hidden symmetry. There's a hidden SO4 symmetry. You see, when you look at this one, there's an obvious symmetry. If you rotate the whole equation with an element in SO4, right, because that acts on S3, keeping the spherical harmonics. So there's an additional hidden symmetry, which is an SO4 symmetry, which had been discovered by Wolfgang Pauli a few years earlier. So remember, SO4 is just SO3 times SO3, and one of the SO3s is just the angular momentum. But there was an additional vector which was preserved, namely what they call the Runge-Lenz vector, which has something to do with the direction from the focal point to the perihelion of the ellipse. That vector is fixed. Anyway, so what we see here from our point of view, we see not only SO4, we see SO4, 1. And we see an Epstein intertwining operator, because the operator on the right-hand side here, this is just a kernel operator, this is just a convolution operator. It's one of those Epstein operators, right? And so we also could calculate by different means. We don't have to go through a lot of circle harmonics. We could find those eigenvalues easily, and we could recover the energy levels of Vladimir Fock. So he was one of the Russian physicists. So he was born in 1998, and so he was one of the physicists that introduced modern physics to the Soviet Union, quantum mechanics, Einstein's relativity, and others. So he was a big name. He was visiting Niels Bohr in 1957 and discussed quantum mechanics with him, and he was trying to convince Niels Bohr that there's it was compatible with the dialectic materialism of Marx, but I think Niels Bohr did not quite agree with that. So I think they never quite agreed on the philosophical interpretations of quantum mechanics. Anyway, so he did this very nice work, and I just want to point out that that what we see here is really a representation of SO4-1, because it's really and so you might wonder which representation is it. And before I answer that question, let me just mention some very recent work, which in many ways is pointing also to the future. Namely, we could imagine similar questions for discrete series of affine symmetric spaces. So what I mean by that, understanding the discrete series and its branching laws, and to what extent could that be explained in terms of discrete series for smaller affine symmetric spaces. So Kobayashi was interested in this. I also did some work with Birgit Svea on this question. And in the algebraic category, much work was done by Kobayashi, by Yoshiki Oshima, with Toshio Oshima. And for the Hilbert category, where there's both discrete and continuous spectrum, there's a remarkable recent paper by Kobayashi. I just want to point this out at the end here. So here the group is OPQ, and the symmetric subgroup is such a product, a little bit like what we had before in the example with Vargas. And the pi you take is a representation in the discrete spectrum of X. So X now is a hyperboloid, OPQ, modular OP minus 1, Q, the hyperboloid. And so the Z is a certain, so Z will give us the infinitesimal character. And this is a representation attached to the smallest elliptic orbit, namely G mod L, where L is an SO2 times the rest. And the discrete H spectrum is given explicitly. This was given earlier by Strickhardt and Rossmann, but here it's given in modern terms. It's given explicitly, and the discrete spectrum of X is given by Rossmann and Strickhardt. And now what Kobayashi did was to find the full discrete spectrum of H. So we do the branching to the group H. So take the subgroup here, symmetric subgroup, and you find that the discrete spectrum is completely describable. It's multiplicity free. It's multiplicity free and has a discrete spectrum if and only if P prime is 0 or P double prime is 0, purely continuous for, well, either P prime Q double prime is 1, 1 or P prime P double prime is 1, 1. So only in very special cases is it purely continuous. And in many cases it's purely discrete and multiplicity free. So you see this happens if P prime is 0. So this happens if the H is an OQ prime, an OP, Q double prime plus Q double prime is Q. So this, I think, in my opinion, this is really a very nice paper. And of course, it points to the future in the sense that you want to study other affine symmetric spaces that have a discrete series, or you might study other homogeneous spaces with a discrete spectrum. So this, of course, is a very deep ongoing work on circle spaces. What also Kobayashi contributed, where we can find the discrete spectrum. So now you may wonder, what about this representation from before? What about if you take SO 4,1? What about if you go back and look at this equation, at this representation? Well, you see this one has the lowest k-type, which is trivial. But indeed, some of the representations here are spherical. So they have a trivial lowest k-type. And indeed, if you take SO41 and its hyperboloid, indeed you find a unique point in the spectrum, which has a trivial lowest k-type. And so you see this group. Now, you may, if you look really closely, there's also an additional symmetry here. In fact, if you take all the bound states here of the hydrogen atom, you'll see a representation not only of SO41 but also of SO4, 2. So this is the famous conformal symmetry of the Kepler problem, and this indeed was also studied by Kobayashi. This is one of these minimal representations. So maybe I'll just end by a little list of some of the references I mentioned. So this last paper, Kobayashi branching laws of unitary representations associated to minimal elliptic orbits for the indefinite orthogonal groups. This is from last year. And the work with Vargas was in Duke 2004 and 2020. And also the work with Joe Wolf on the Borel-Siebenthal discrete series was in Journal of D Theory 2010. Yes, I think I'll end with this. Thank you and congratulations, Kobayashi Sensei.